So the choke, and a lot of people have heard the term choke, is the component at the top of the air horn of the carburetor. So it's this little flapper right here at the very top. And what it does is it changes the low pressure event from here at the throttle plate to up here at the choke, which allows us to pull fuel out of our main metering, thus enriching the mixture on a cold engine. So the choke, yes, it's blocking air, but the engine, if it's running, still has to pull in the same amount of air. So if my engine's doing 800 RPM, it needs that much air, regardless of the choke position. The difference is that we are creating the low pressure area below the choke instead of creating the low pressure area below the throttle plate. This allows us to use vacuum to pull fuel out of our main metering as well as our idle and transition ports. So we're able to get more fuel into the engine, a richer mixture. Richer mixtures burn easier, which is very important on a cold engine. So that is why we have the choke. So even on small engines, you'll have a choke and you maybe turn it on just so you can pull it and start it. Then you have to turn the choke off right away because it'll flood out. It actually runs too rich. But what that choke does is allows it to give that extra fuel for starting, and a rich mixture, again, burns easier. And so that's why they're using that. So chokes in the early days were manual, where we had to remember to turn the choke off. We had a cable attached to it. Once emission controls came out, we started using a bimetallic spring. Where bimetallic spring is a spring made out of two pieces of metal. So when it expands and contracts, it actually twists and untwists. And that spring would be used either use electricity or used heat from the exhaust to make it wind and unwind to open and close the choke. So that's called an automatic choke. And that's what we've used on emission control vehicles going back to the 70s. So in the 60s, you'd see some manual chokes quickly because people would drive with the choke on. The car's polluting a lot if the choke's on or on part way. People would use the choke to compensate for a worn carburetor that might not be working correctly, again, causing excessive emissions. So that's why we went to that automatic choke. In order to set the choke on a carbureted vehicle, you have to put your foot all the way to the floor and back once. And what that does is it takes the linkage off the stop on the throttle right here, this little kicker arm that you see, which is the fast idle cam, and allows it to close. The spring is going to close the choke. And that's also why if you start it up and don't touch the throttle, the idle will start out fairly low and get higher and higher and higher until you snap the throttle. Then it'll open up, because that bimetal spring is trying to open the top, but it's still held up on that high idle cam until you kick it. Then it'll move and it'll come back down to low idle. So that's how chokes work. That's what we're doing with them. Chokes do go bad. I've replaced a lot of they call it a choke thermostat. It's the little bimetal spring. They're round in plastic normally. That actually opens and closes the choke, and they go bad all the time. So people don't know how to test them or don't realize that that's a component that needs to be tested. So they try to adjust the carburetor to make up for either the choke staying on all the time or the choke never coming on, trying to get the car to run. So a choke thermostat has to move between cold and hot. So if I go out to a cold engine, the coil should be in one position with the rod, and as the engine heats up, that rod should move. If it doesn't, that's a problem. We also make different choke testers. I have one that has hot air comes out one side, cold air comes out the other. In the real old days, we used to use a can of Freon because Freon was super cheap. And we would just have a can of Freon. We'd open up the Freon valve and freeze it and watch it move one way and then watch it heat up. Those days are long gone. Obviously, you can't buy Freon anymore, and it was bad for the environment and so on. But that's how we used to do it. But the whole concept is you need to make it cold, and then you watch it get hot, and it should move and it should change the position of the choke. If it doesn't, then the choke thermostat's bad. And that's a high failure item. I've replaced tons of those on carburetors. Again, why would I rebuild the whole carburetor if all it needs is a choke thermostat? So that's where understanding what the different components do is really important. So you don't have to throw your hands up and go, gee, it needs everything, or I've rebuilt it 3 times and it still has the same problem. Well, if you don't know what is causing the problem, how are you going to fix it? And if you know what causes the problem, do you really need to replace the whole thing, or can we just go in and fix that one part? So that's where I spend the time on these systems. So, however, most are controlled automatically. So the valve is closed when the engine is cold and opens progressively as it warms up. And overuse produces rich mixtures, horrible fuel economy, and so on. Some later model carburetors used a cable operated choke with a spring loaded choke release. This is Toyota Land Cruiser. They were the last one to use a manual choke you would turn on, but it would turn itself off. And that's how they got away with it. And that was on the carbureted Land Cruisers. So you hear the talk about barrels in a carburetor, a 2-barrel carburetor, a 4-barrel carburetor, right? So a barrel has to do with how many of these cutaways we looked at. So we saw the Venturi, we saw the idle port, we saw that stuff. So the question is, how many of those do we have in the carburetor? Do we only have one place that air goes in? Do we have 2 places with 2 throttle plates that air goes in? Do we have 3? Do we have 4? Any of those is an option. Generally, smaller engines would have a 1 or 2-barrel carburetor. A big V8 would have a 4-barrel carburetor. The notable exception is Honda, which used a 3-barrel carburetor even on their small engines. And that was to give it better control, better performance. So extra barrels improve performance. I can pull more air into the engine. So I'm limited. My engine power is limited by how much air I can put into it. So by having extra barrels that I can open up or extra ways of air getting the engine, I can increase the volumetric efficiency, allowing the engine to run at a higher speed or to feed a bigger engine or both. A carburetor that is too large for an engine, though, actually reduces power. So the size of the carburetor and the size of the exhaust both have to be matched to each other, as well as the mechanical part of the engine. So in other words, I can put too big of an exhaust on an engine. I can put too big of a carburetor on an engine, just like I can put too small of a carburetor or too small of an exhaust. So these things are all about flow. Remember, our engine's an air pump. So I'm trying to pull air in this case through a carburetor, and I'm going to put out air out through my exhaust system. So it doesn't make any sense to have an exhaust system that's much bigger than what the amount of air that I can put through the engine. Aside from wasted money, it actually detunes the engine because it reduces back pressure in the exhaust. Same thing with too big of a carburetor. I'm going to flow too much air, too much fuel for the engine. It's not going to run right. I'm not going to be able to generate the vacuum I need to pull the correct amount of fuel for the air coming in. I'm going to have some lean issues, other things going on. So 2-barrel carburetors have 2 outlets into the intake manifold, come in 2 basic designs. So 2-barrel carburetors come 2 different ways. One is where we have a primary barrel and a secondary barrel. So the primary barrel is the only side with a choke, and that's the only side that's used under normal operation unless you put your foot really down close to the floor. Then the second barrel would open up and flow fuel. We also have 2-barrel carburetors that have 2 primary barrels, and that's easy to tell by looking at the top of the carburetor. And if there's a choke plate over both sides, not just one side, that means that both the barrels are a primary barrel, because only primary barrels get the choke. Secondary barrels don't need the choke. They're only for high-end performance, high-end power. So if I'm looking down a little 2-barrel carburetor and the choke feeds both barrels, guess what? It's their 2 primary barrels. If it only feeds one, we have a primary and a secondary barrel, which means that I'm not going to see gasoline coming out that secondary barrel at idle. And the throttle plate for that secondary barrel should be closed at idle. If it's open, that's a problem. The carburetor is not adjusted correctly. Here's a 4-barrel carburetor, and you can see here we have the 2 primary barrels and then the 2 secondary barrels. So these 2 primary barrels are both fairly small. They have the choke. You see how much bigger these secondary barrels are, and they're designed to only open over a certain amount of airflow, a certain amount of load. And so there's a couple of different ways we can operate the secondaries. One is with vacuum, the other is with mechanical linkage, but both of which allow a delay. So these should never be open at idle. If these are open at idle, it'll cause a vehicle to run lean because there's no idle ports here. So if these are open, you have air going in the engine with no fuel. Car's running lean. So that's, again, that's a simple adjustment issue. But this is what they mean by a 4-barrel carburetor. One of the things we started to do is we started to use the computer to control carburetors, and it worked marginally well for the time. So by the use of a solenoid to control main metering. So And so what we would do is we would use a solenoid, and depending on the system, it may even control the idle circuit. Well, carburetors by design are going to naturally flow fuel into the engine. So unlike our fuel injected systems that I can put all the fuel I want in the rail under as much pressure as I want, unless I turn on the solenoid, no fuel gets in the engine. Carburetors are just the opposite. Carburetors, fuel is going to go in the engine unless I stop it. So we use solenoids on these feedback carburetors to try to limit the amount of fuel going in the engine. So you can see where this is kind of a losing battle. It's really a backward strategy from what's efficient. So this allowed them to get many more years out of carburetors on vehicles, but these were really kind of horrible, to put it bluntly. A lot of different ways we did this, some different solenoids, air blades. I mean, some of them got really, really complicated. Again, trying to make a carburetor work when we should have just gone to fuel injection. But there are still feedback carburetors out there. Again, these were used into the 80s. And in the case of, was it Mazda up until 94. So we did see some feedback carburetors pretty late. Hopefully you won't have one in the shop. If you do, if you see electrical connections going to the carburetor and the vehicle has an oxygen sensor, that is a feedback carburetor. That means the computer is trying to control the amount of fuel coming out of it. So not only do we have all of our mechanical components we've already talked about, we have an electrical solenoid or solenoids that are trying to control the fuel delivery. And so that's a whole nother set of testing. I don't get too far into carburetors in this class because the reality is the people my age that know about carburetors that have already suffered through the decades of them are the ones that are probably working on them. And to try to get that learning curve at this point is really a bad investment for the most part, because there just isn't that many carburetors out there. That being said, I do have a former student who's working at a shop, and they do a lot of carburetors because they do a lot of hot rods. It's a big part of their business. So he was able to take the foundation that he learned in this class, and then under mentorship of the old guy who owns the shop, he's rebuilding carburetors. He's doing that. He's learning that skill, but that's really the exception and not the rule. And that's something that really, if you end up in a shop that does these a lot or specializes in these, you have enough foundation now to speak the language. And then from there, it's what? Hands-on application, practice. And that's where you need that mentorship in a shop. So that's why I really stop here on carburetors, including feedback diagnosis, because we, for the most part, just don't do it much anymore. Even as a smog repair tech, I only do a couple feedback carburetors a year anymore on smog failures. I mean, there just isn't that many of them out there. So that's why I don't invest a lot of time. I just want to share the concept. So a mechanical fuel pump, we use mechanical fuel pumps with carburetors. Some late carburetors did have electric fuel pumps. The disadvantage of a mechanical fuel pump is that it uses vacuum to pull fuel from the tank to the fuel pump. So because it's under vacuum, fuel is going to boil at a lower temperature and we get vapor lock. Very common on trucks, motorhomes, things like that. The other issue we have is that because we're using vacuum to pull the fuel, if I have any cracks in hoses, I'm going to pull air in through the crack because it weighs less than the fuel in the tank. So I can have a car that doesn't run because I don't have any fuel. I put a new fuel pump on it. It still doesn't run. It still doesn't have any fuel. Because why? Because there's a crack in the hose and we're pulling air, which is lighter than we're pulling fuel. So when we diagnose these systems, we really have to isolate the pump and test what the pump's doing. Don't assume because I don't have fuel, it's a bad pump. I have to test and make sure that I'm able to pull fuel under vacuum through that hose coming up, and that I don't have any cracks there. I got to make sure that my fuel filter is not plugged. Now on these systems, the fuel filter can be on the pressure side where I've got, 3 to 5 PSI pushing fuel through it. Or I could be on my vacuum side where I'm using vacuum trying to pull fuel through a filter. So if that filter restricts, it's really hard to get fuel through it. And we have cars that put them in both places. So these are normally mounted to the cylinder head, timing cover, engine block, and they are driven off a lobe on the camshaft. and it uses a little spring-loaded pump, and there's two valves in here. And they're just little check valves, little spring valves. So we pull fuel in. So when this pulls down, it creates a vacuum, and it opens this valve, allows fuel to come in. When it goes up, it forces this valve closed, but pushes this valve open, which pushes fuel up towards the carburetor. So these have to create pressure on this side, and you'll find pressure specs. However, they also need to create vacuum and hold vacuum on this side. And the mistake many people make when they test these is they do the pressure test. Oh, I don't have any pressure. I must have a bad fuel pump. Hold on. You may have a bad fuel pump. You probably do have a bad fuel pump, but let's double check and see what's going on here with vacuum. The other is you might think, I have pressure, so my pump's good. But if it can't generate vacuum, it can't pull fuel from the tank. So you have to check both. So you'll have them that test good on the pressure side, but not good on the vacuum side. And these should also hold vacuum. So if it pulls up and it pulls up 15 inches of mercury, it should hold 15 inches of mercury. If it's bleeding down, going back and forth, you have a bad check valve right here. And a lot of times debris or contaminants will get in the check valve and hold it partly open. So that prevents it from being able to pull fuel. So I can have pressure, but no fuel. I can have no pressure, either because the check valves or because we're pulling air. I have good vacuum, but I'm pulling air, and the fuel pump is not able to generate that 5 to 7 PSI with just air, just because of how it's designed. And so, gee, I think I have a bad pump. No, the vacuum's good. We're just not pulling fuel. For those that are familiar with the pump, you might have heard the term prime the pump, where you have pumps that are designed for liquid that you can pump with air and they don't do anything, but as soon as you put liquid in them, they work great. So that's some of the issues we have with diagnosing these. In the old days, we used to rebuild these. Now they're just all serviced as a unit. They have a spacer on some cars, especially Asian vehicles, that goes between the fuel pump and the engine. If you leave the spacer out, you will have too much fuel pressure because it moves the arm here further up. So the arm moves more up and down, creating more pressure, and that pressure will overcome the needleless seat and flood the carburetor. So it's important that you look when you take these off. If there's a spacer plate, the spacer plates are only about 1/4 of an inch wide. They're pretty skinny, only about like this thick. And if it's dirty, it's real easy to miss that that's there. So that's something you want to inspect for. So anytime we replace a part, whether it's a fuel pump or any other part, we always want to closely inspect the parts we're taking off and compare those parts to the parts we're putting on. So when less fuel is needed, pressure builds up in the fuel line to the carburetor and in the pumping chamber. As fuel circulates, it cools the pump and lines, reducing the chance of vapor lock. So we don't vapor lock normally on the pressure side. We can, but it's unusual. We are at 3 to 5 PSI. It's harder to vapor lock there. It can. My off-road Jeep, I run it down about 1/2 PSI between the pump and the carburetor, and that will vapor lock. If I'm at any kind of altitude and I shut the engine off, it'll boil all the fuel in there pretty quickly. And I have to turn the regulator to put full pressure on it, start it up, then turn the regulator back down in order to run 1/2 PSI. But it's pretty amazing. I'm running a V8 engine on about 1/2 PSI of fuel. Now, granted, I'm not racing with it. I'm rock crawling with it. And occasionally I need to run the engine RPM up higher. But it really gives you an idea of how little fuel we really need to run the engine. So these systems, 3 to 5 PSI doesn't sound like a lot. It's low pressure, high volume, and more than enough to run these engines. We had low pressure electric fuel pumps that mimicked our mechanical pump. So these ones will go tick, 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 tick. And you have a little electrical connection and switching points and linkage and a diaphragm, the plunger that goes up and down. And when pressure is not equal on both sides here, it'll pump. Once pressure equalizes on both sides here, it'll stop pumping until fuel is used, then it pumps again. So these were used by some manufacturers on late carburetor and early throttle body fuel injection systems, low pressure systems like GM. These also can be used as a replacement for an older vehicle that the inside the engine where the fuel pump rides on the cam, sometimes the cam will go flat. So you have a choice of replacing the camshaft, or you can install an electric pump and then disconnect the hoses off of this and route them to that electric pump. And it saves you the money of putting a camshaft in it. And that used to be fairly common back in the day when a lot of vehicles were run this way and we had bad oils, and if people didn't take care of it, their camshafts would go flat. But that is something you can do. So it just talks a little bit about the circuit on it and how it operates. I think that is really it that I had for this section. The book has a bunch of skill drills in it, kind of some different pictures and tests. It has some good animations and videos in the book on it. So I'll leave that to the book. Any questions on what we went over so far this morning? Okay, so we're going to get into some fun stuff now. And we're going to talk about how we control the fuel, why we control the fuel, how fuel control affects emissions. And then we're also going to be looking at our 3 types of oxygen sensors. So this PowerPoint presentation, which let me see if I've turned it on in Zoom. I might not, I mean in Canvas. Don't think I have yet. There we go. Okay, I just turned on the PowerPoint presentation for those of you that want to follow along in it. So everything we do is really about fuel control. This is the computer's primary goal, is to control fuel. So we're probably not going to get into all the oxygen sensors today. We're going to save them for next week, and that's fine. This is a fairly big presentation. So I'm going to talk about air-fuel ratio. We've talked about it some. We've talked about stoichiometry. So now I'm going to move it along and really show how it affects emissions. We've already talked about lambda. So I have slides in here on lambda. I'm not going to go over them again. They're basically the same slides we've already covered. I moved them out of this presentation into the book's presentation because the book was talking about it. So I wanted to put that in there. And then we're going to look at our 3 types of sensors, which is a zirconia sensor, a titania sensor, and an air fuel ratio or wide band sensor. And so we're going to look at how they work and some different ways we have of testing them. So air fuel ratio is the amount of air primarily made of nitrogen and oxygen compared to the amount of fuel. For the purpose of this discussion, is going to be gasoline, which is hydrocarbon. The ideal air fuel mixture for gasoline is 14.71 pounds of air for every pound of fuel, which is normally displayed as 14.7 to 1. So when we look at where our gases come from, we have fuel and we have air. We're going to mix it inside our air pump. And ideally, I want to make water, H2O, and I want to make CO2, carbon dioxide. Those are the 2 things I want to make in my internal combustion engine. If I have hydrocarbons coming out the tailpipe, that's because I haven't burned all the fuel. If I have carbon monoxide coming out the tailpipe, that means I have a lack of oxygen. I don't have enough oxygen to make carbon dioxide. If I have oxygen coming out the tailpipe, that means that one of 2 things is happening. Either I'm putting too much oxygen in, or the oxygen I'm putting into the engine has not been combined with my hydrocarbon in a way that I can oxidize the hydrocarbon. So that could be from low compression, a bad spark plug, those kinds of things. Oxide nitrogen, or NOx, is where we have excessive heat over 2,500 degrees under pressure causing oxygen and nitrogen to bond together. So a rich air fuel mixture, there is less than 14.71 pounds of air available for every pound of fuel. This can result in misfires and incomplete combustion, creating higher CO and HC levels. Normally, CO2 would be created by combustion, but with a lack of oxygen, there is not enough to completely oxidize the carbon, resulting in incomplete combustion, and a misfire allowing unburned hydrocarbons to reach the exhaust stream. In a lean air-fuel ratio, where there is more than 14.71 pounds of air available for every pound of fuel, this can result in misfires and excessive heat, causing higher hydrocarbons and NOx emissions. When the air volume is too great for the amount of fuel introduced into the combustion chamber, all the oxygen will be used to oxidize hydrocarbons. However, since the mixture is out of balance, there will be some hydrocarbons without oxidation. This results in hydrocarbons reaching the exhaust stream. So what happens is the oxygen interrupts the burn, basically. The controlled explosion we have inside the combustion chamber. So even though we have enough oxygen to oxidize all the hydrocarbon, the flame front, the heat that is used to create the oxidation, is not able to get to everything because the oxygen is actually insulating some of the hydrocarbon from that heat and not allowing it to be oxidized. When the air fuel mixture is lean, the temperature of the burn is increased due to increased oxidation. This heat is contained for a short period of time in the combustion chamber. When the temperature exceeds 2,500 degrees Fahrenheit, the oxygen and nitrogen molecules from the air are bonded to create oxides of nitrogen. So we're going to look at a few air fuel ratio charts and put some numbers to it. And so here we have 14.7 to 1. Which is our deal. I have 15% CO2, under 400 parts per million of NOx, under 50 parts per million of hydrocarbons, less than 0.5% CO, and less than 1% O2. So this is in a controllable range. Remember, my engine is not 100% efficient. I need a catalytic converter to clean this stuff up before it gets to the atmosphere. This is just where things are manageable for the catalytic converter. So the purpose of this is to show what happens to the exhaust levels when the average air-fuel ratio goes richer or leaner than the preferred range of 14.4 to 15.0. This vertical line represents a specific air-fuel ratio, in this case 14.7 to 1. And each dot indicates the gas level of the air-fuel ratio, where the line represents a stoichiometric ratio. CO2 is at its highest point, 15%. NOx is in a normal range below 400 parts per million. Hydrocarbons are below 50 parts per million. Oxygen less than 1%, and carbon monoxide less than 0.5%. So now we're going to go slightly rich. And so this is 14.3. So this is, again, barely outside our 0.980 lambda. And so now they indicate a slightly rich mixture, and let's look and see what happens to the emissions. My CO2 is dropped. It is now down at 14%. My NOx is dropped because a richer mixture burns cooler. Hydrocarbons have gone up because we're not burning all the fuel. CO has gone up because I have a lack of oxygen. And O2 has gone down again because of that lack of oxygen. If I go very rich, now I'm down to 13 to 1. So now let's look at what the exhaust gases did. I'm down to 12.5% CO2, under 250 parts per million NOx, hydrocarbons up 100 to 140 parts per million, CO at 5%, and O2 at 0.1%. And again, these are just examples showing how it goes in reality. I'd probably have much higher hydrocarbons than that. So now we're back to stoichiometric, and we're going to go slightly lean. So we go slightly lean just outside our fuel control range. And now we're at 15 to 1. So we can see here CO2 again dropped. NOx went up, almost doubled. Hydrocarbons is up. O2 is up 2%. And CO is down very, very low. Remember, CO is a lack of oxygen. I have plenty of oxygen here. As I go very lean, 16-1. I now have 13% CO2. Again, CO2 continued to drop because CO2 is my efficiency gas. It's going to be highest when I'm at stoichiometric. NOx is peaked at 1,120 parts per million. Hydrocarbons are up, oxygen is up, and CO is at 0. So you can see how mixture really affects these gases. It's kind of a little bit of a teeter-tottering effect almost. If I go one way, certain gases go up and other gases go down. As I go the other way, other gases go up and some gases go down. So there's an effect as we move back and forth across fuel control. So in order for a car to run clean, which is what we want, because we don't want smog. I grew up in California where we had smog days. You didn't get PE, your eyes and throat burned walking home from school. We don't want to go back to that. So fuel control is a big part of why we have cars that run as clean as they do and get as good a mileage as they do. So which emission will not go up when the mixture is too lean?
Number one.
Number one, absolutely. Because CO2 is highest when I'm stoichiometric. So if I go rich or lean, it's going to go down. It's always highest when I'm at stoichiometric. And if I'm not stoichiometric, it goes down. However, if I go lean, NOx, O2, and HC all go up. What emission goes up with a rich mixture?
Number three.
Number three, CO goes up with a rich mixture. CO is a lack of oxygen. As I'm running rich, I have less oxygen, therefore that gas will increase. NOx, number one, will go down because a rich mixture runs cooler, therefore I'll make less NOx, if any NOx at all. What emission is at its highest when the mixture is stoichiometric?
Hydrocarbon.
No, hydrocarbon's at its lowest when we're at stoichiometric. Hydrocarbon is unburned fuel, and I burn fuel most efficiently when I'm close to stoichiometric.
So it's carbon dioxide, CO2.
Carbon dioxide, CO2, absolutely. It's at its highest because it's my efficiency gas. So when my engine's most efficient, it's going to be at its highest. So you've heard me throw some exhaust gas terms here. I have a slide here that actually goes through them one at a time. So hydrocarbons is unburned fuel. Carbon monoxide, lack of oxygen. If I had more oxygen, I could make carbon dioxide, which is what I want. Oxides of nitrogen is excessive heat. Carbon dioxide, my efficiency gas, and oxygen is my balance gas. So if I have too much oxygen, I'm lean. If I don't have enough oxygen, I'm rich. So we're really balancing oxygen here. So that's my balance gas. So I do also have a chart here that shows the gases. Here's my 14.7-1. And here is my CO2, my NOx, my CO, my HC, which is kind of like a smile, and then my oxygen. And this chart, when I teach, students to go prepare for their smog exams, stuff like that, I actually make the students memorize this chart because this is such a valuable tool when you're answering test questions, because it's easy to get confused. What goes up here? What goes down here? How does that affect that emission? It's easy to get confused and turned around. But this chart's pretty easy to memorize, and it really is a useful tool. And it was always interesting. After test night, I go around, look at the tables, or look at somewhere on the test. And sure enough, they drew this little chart out and they used it to answer their questions. So it is a real effective way of learning gas relationships, because it is easy to get turned around or you're trying to remember, but having something visual you can look at and refer to is really huge. So this chart, and I've seen quite a few of these charts, this one's probably the best, not just probably is the best I've found. There's a couple things I tweak on it just a hair, but it's still the best of any of the charts I found. A lot of them are way, way off. So this is a good chart here. What emission can be described as excessive heat? No one? Should I go back to the previous slide?
Number 3.
Okay. Yeah, number 3, NOx. NOx is excessive heat. So we're going to talk about lambda a little bit here in the PowerPoints. I'm going to jump ahead on that a little bit and just move to some lambda questions. If there is an exhaust leak, the lambda calculation will be artificially what? How's the exhaust leak going to affect my lambda calculation?
The car will run rich.
Well, the car could run rich, but the lambda calculation will actually be lean, because we're going to pull in oxygen from the atmosphere into the exhaust, and then we're going to be measuring that as if it went through the engine. So if I have an exhaust leak, my lambda calculation will be artificially lean. So if I have a mixture and I test it and I come up as being really lean, one of the things on my list to check needs to be exhaust leaks before I go any further with my diagnosis. Which of the following is a rich lambda value?
Number 2.
Number
Also,
two.
number 3.
Number 3, yes. Number 3 would be rich. Remember, because the ratio is oxygen available over oxygen required. So if I have more oxygen required than I have, my ratio will be less than 1. So that's a rich mixture. So 0.98 is rich. High NOx can be caused by which lambda value?
Number
Number
1.
1.
No, number 1 is stoichiometric, right? Isn't that where I want to be? Number 1 is perfect lambda. So that's going to be where NOx is still manageable and CO2 is peaked.
So it's 95.
Well, let's go back and look at our chart. So here is NOx. So here's 1 lambda. So now I need to remember, is 1.04 rich or lean?
Lean.
Lean, right. So when I go lean, what happens to NOx? It goes up, doesn't it?
Yeah.
But if I go 0.95, that's rich. What happens to NOx? It goes down.
It's down.
You see where this chart can be really helpful? So the answer to our question would be 2. 1.04 lambda. That's our only lean mixture. Lean mixtures burn hotter. Hotter mixtures make more NOx. High CO emissions can be caused by which lambda value? So if we think about the definition of CO, and then we think about which lambda value is rich and which lambda value is lean, we should be able to get there.
It will be 1 again.
Well, it's not going to be 1 because 1 is stoichiometric. 1 is where we want to be. So 1 is not going to cause excessive emissions of anything. So it's down to either has to be 1.05 or 0.94. So CO is, what's that?
You say 0.94?
It has to be 0.94 because CO is a lack of oxygen, which just by its definition means it's probably a rich mixture. So in order to have a rich mixture, my ratio has to be less than 1 lambda, which would be my 0.94 answer. Okay, so let's talk about some oxygen detecting sensors. So these are located in the exhaust stream, provide feedback information to the PCM, ECM, whatever you want to call it, about the oxygen content in the exhaust. Now, what I'll tell you is they do not directly measure oxygen content. They actually measure lambda. They're actually lambda sensors. We call them oxygen sensors because no one knew what lambda was. So that is kind of where we get into a definition thing. But these sensors, they may generate their own signal in the case of a zirconium sensor. There are 3 types of sensors we use. We use zirconium sensors. That is the most common sensor used before the catalytic converter up until the early 2000s. It is still the only sensor used after the catalytic converter. So zirconium sensors are with us. They're probably going to be with us for quite some time. Titania sensors were only used on some Nissan and Toyota products in the 80s and into early 90s, and by Jeep products in the late 80s, early 90s. Air fuel ratio sensors started being used around late 90s and are the most common sensor in front of the catalytic converter today. Often called a wideband O2 sensor or a broadband plein air sensor. So they have quite a few different names for them, but we normally just call them air fuel ratio sensors or AF sensors. So here's a zirconium sensor cut in half, not much to see here. What you do see is we have little holes that allow exhaust to be brought in here. And then we have a ceramic element where we're able to have exhaust gas attack it. We're gonna have a wafer inside here that actually generates a voltage. So if we look at this, come on. Why are we not moving? There we go. So here, the outside of the threads is grounded. On newer sensors since the 1980s, we actually ground. We don't ground through the threads anymore. We ground through the wire to the sensor because rust and corrosion would cause a bad ground, which would cause the sensor not to work right. So there's a platinum coating in here. Platinum is already an active material along with the ceramic zirconia element. So we have a positive terminal, negative terminal. And what this does is it actually generates voltage. Pretty cool. So it's actually able to generate voltage, and based on the voltage it generates, it tells the computer basically kind of what the mixture is. Is it rich or is it lean? It's not telling it precisely what it is. It's only telling it rich, lean, rich, lean. It's not able to tell it exactly what it is. Just, is it rich? Is it less than 1 lambda or is it more than 1 lambda is all it can tell it. So the internal temperature must be kept above 600 degrees in order to operate. So here's an older vehicle with a single wire O2 sensor. So this O2 sensor would only work when the exhaust was hot. There was no way of making it get hot faster. These sensors would cool off when you were at a stoplight or idling for a long time. So we use these in early O2 sensors. However, Saturn used them up until like 98. So we did see some of these come into some early OBD2 stuff. I don't know quite how they got away with it. But these are around quite a while. Again, the issue with this is that I have to complete the circuit by grounding it through the manifold. So any kind of rust, corrosion, things like that could affect how the sensor works. What we see today are normally 4-wire oxygen sensors. So 2 wires here are for the sensor itself, power and ground. The other 2 wires are for the heater. So these actually have a heater in them to heat the sensor up and keep it hot so that it'll stay working while the car is idling. So this is a 4-wire zirconium sensor. Now you have to be careful because the 4-wire zirconium sensor can look identical to a 4-wire air fuel ratio sensor. Matter of fact, I can't tell the difference looking at them. I would need to get the part number off of it and run the part number because they can look identical. So we never want to just go, gee, it looks the same. We always match up part numbers on sensors. And the advantage of this is it doesn't depend on how good my electrical connection is at the threads at the bottom, because my electrical ground connection is through the wires. So with my O2 sensor, we have about 21% oxygen in the atmosphere. If I have high oxygen content or above 1 lambda in the exhaust stream, I will have less than 300 millivolts. On the other hand, if I am rich below 1 lambda, I would have over 600 millivolts. And this is generated by the electron flow through the platinum and zirconium wafer. So it needs carbon in order to have the catalytic reaction happen. So these are not just oxygen sensors. What they do is they measure, am I above 1 lambda or am I below 1 lambda? And with that, the computer takes that as a binary. And if I spend half my time rich and half my time lean, I should be at 1 lambda. So that's really how the computer works. It's just looking at time. How much time am I spending rich? How much time am I spending lean? Did I balance it out? If I did, I should be in good fuel control. And that's how these systems worked forever and largely continue to work today, except for today we have a much wider range of what we can see. So my zirconium sensor generates 0 to 1 volts depending on relative O2 content in the exhaust. 400 millivolts is used as a switch point. Below 450 millivolts, exhaust is lean. Above 450 millivolts, the exhaust is rich. The sensor switches very fast. It must switch under 100 milliseconds when tested with propane. We normally see them test at 35, 36 milliseconds. By 50 milliseconds, I'm throwing them away. So 100 milliseconds is really slow for one of these. And they operate at 600 degrees Fahrenheit. So here is a chart. So here's lambda at the bottom. So here's 1 lambda. This is 0.975 lambda. This is 1.025 lambda. And we can see my voltage, which goes from high to low, happens right at 1 lambda. So this is truly a lambda sensor. So, and that's really important when it comes to fixing cars. You may be thinking, you know, everyone calls it an oxygen sensor. Why is he calling it a lambda sensor? Because if I want to fix modern vehicles, if I want to know if a vehicle is running rich or lean by looking at the rear sensor, if I want to understand what the converter is doing, if I want to be able to test things, I need to understand this is a lambda sensor. It's not just measuring oxygen. It is measuring what the mixture is. And that's really its power. And that's why these are such a powerful diagnostic tool today. That's why we use them for a lot of diagnostics. That's why the computer relies so heavily on them. So here is an oxygen sensor pattern. And you can see it's constantly going lean, rich, lean, rich, lean, rich, lean. It goes lean and rich because the computer is making it go lean and rich. So as soon as it goes lean, the computer adds fuel to make it go rich. As soon as it's rich, the computer takes away fuel to make it go lean. It does that in order for the catalytic converter to work. If we didn't go rich, lean, rich, lean, rich, lean, the catalytic converter would not work. So although we have the technology that I could make this, hey, I want to be at 450 millivolts and just make a flat line there, we could do that. We have the technology to do that. The problem is the catalytic converter won't work. And as we know, the catalytic converter is what makes our 95% efficient engine come out close to 100% efficient as far as oxidizing all of our hydrocarbons and not having NOx formed and all that stuff. So a modern vehicle that's running correctly with a good catalytic converter, I'll actually put zeros out the tailpipe. 0 HC, 0 CO, 0 NOx, and about 15% CO2. So when a gasoline engine is running efficiently and the catalytic converter is working properly, we're really only putting out water and carbon dioxide, along with certainly nitrogen that we haven't done anything with, which is really the goal. I mean, we're hitting many times when I test these vehicles, almost that perfect goal of this car is not putting anything out at the level of the test equipment that we're using. It's zeros, it's zeroed out across the board. That's pretty phenomenal, really, when you think about it, especially when you compare it to cars 30 years ago, 40 years ago, 50 years ago, and how dirty they were. So it is really phenomenal how much cleaner things are now. So that's why the oxygen sensor is oscillating richly and richly. So when the zirconium O2 sensor voltage is 600 millivolts, what is the air fuel ratio?
Will be rich.
It'll be rich, absolutely. Over 450 is rich. So we also had titania sensors, and fortunately they didn't use these very long. If you're working on a Nissan or Toyota, you might not even know you have one, and you're going to diagnose it like a zirconium sensor and plug in a new sensor that the parts store sells you and go along and probably not even know that you were working with a titania sensor. If you're working on a Jeep 87 to 90, these are your Cherokees with a Renix, which is a Renault computer system. They use a 5 volt reference. So that very quickly, when you hook a lap scope up and you see 5 volts, you know something's different. So unlike zirconia that generates the voltage, titania changes its resistance based on lambda. Kind of cool. So if I look here at the 5 volt sensor, I have a VREF of 5 volts with a fixed resistor, comes through a variable resistor to ground. Isn't that like our ECT signal, right? 5 volts resistor, another resistor that's variable and ground. Isn't that exactly what our ECT circuit was, IAT circuit? So electrically, this is working exactly like that. The difference is we have a heater element here because this will only work when it's hot. So they have a heater built into them. And we pull our signal return for the computer off the wire between the sensor and the computer, not between the sensor and ground. So very similar to a ECT signal or IAT signal from a circuit standpoint, it's identical. From a testing standpoint, these are a little confusing because on the Jeeps, a lean mixture is high voltage and a rich mixture is low voltage. But on a Toyota, lean mixture is low voltage, rich mixture is high voltage. Well, that's because of where they put the reference voltage. Here you have the reference voltage, the variable resistor, the signal wire, the fixed resistor, and then ground. So we're controlling it on the ground side here, control it compared to on the power side here. That's why it's inverted. So the circuit's doing the same thing. We're just measuring the ground side of the circuit versus the power side of the circuit. So the key thing is high oxygen content equals high sensor resistance. That's why I say you can work on these Toyotas and Nissans, and this is like old stuff, 80s, early 90s. Because it's 0 to 1 volt, and because a lean mixture is low and a rich mixture is high, you're going to test it just like you do a normal O2 sensor. And if it doesn't work, you're going to replace it. You'll probably never know you're working on a titania sensor. It's just not that big a deal. On the Jeeps, 5 volts instantly get your attention. Hey, it works opposite. Well, you know what? I'm not going to test you on this. It'd be dumb to test you on this. These cars are all but gone. These cars are almost all but gone. And it's only one model for 3 years, basically. All I want you to know is, hey, you know, if you're working on a Jeep and you see 5 volts on O2 sensor, go get the book because you're not working on a zirconium sensor. So really all I'm looking for is that you know a titania sensor exists at this point. We do see titania used in some other applications, but it's all inside things for engineering reasons. It's nothing we're testing. So it's kind of cool geek out stuff, but it's nothing that is necessarily going to help you fix the car. It just might explain why things work once you get to a certain level. So I just want, I put these in here because they do exist. I want you to at least have heard of them, but this is not something I would waste a quiz or test question on. You see I had a lot of animations in here when I used to spend more time on these. This is a shielding ground here. This is for the signal. You see they both have a waveform, just like we're used to seeing a waveform. That's why I say on the Toyotas and Nissans, they're going to look just like a zirconium sensor. So let's look at some air-fuel ratio sensor operation. So this is also a wideband or broadband planaire air-fuel ratio sensor. And what it is, it's actually two zirconium sensors built into one housing. And so the one I'm going to show you here that we're going to walk through the animation on is a little overly simplified, and it's also more of a Bosch style. So the sensor I'm showing you doesn't really exist from a connector standpoint. It's more about explaining the theory. So a regular O2 sensor, zirconium sensor, is constructed with platinum electrodes, two, and a zirconium dielement. So, zirconium dioxide element between the electrodes. We commonly call that the wafer. And it's kind of like one of those wafer cookies. So when we have electron flow through the wafer, voltage is generated. So if I look at the exhaust system, as oxygen displaces the oxygen, exhaust displaces the oxygen in the exhaust pipe, the platinum electrodes react, catalytic reaction, to the potential difference in oxygen content between the outside air and the inside of the exhaust pipe. So we're going to drop some down here. This potential difference creates an electrical signal. So it went down. The difference between what's in the exhaust and the fresh air, there's electron flow that generates a voltage. So instead of just lighting up a light bulb, we're going to connect to a powertrain control module or an engine control module. So the current is developed because the platinum plate in the exhaust stream will draw oxygen ions out of the fresh air side to the exhaust as part of the catalytic reaction. It is the transfer of ions through the platinum plates that creates the current flow. So this is how it works as a lambda sensor. If I don't have oxygen in the exhaust, the catalytic reaction is with carbon. So I have to draw the oxygen from outside in order to oxidize the carbon I'm having a catalytic reaction with. That's what generates the voltage on a rich mixture. On a lean mixture, there's plenty of oxygen in the exhaust to have the catalytic reaction on the wafer with the carbon. Therefore, I don't need to draw any oxygen from the outside. So you see, it's really not measuring oxygen or balancing oxygen. You think about it, we have almost 21% oxygen in the atmosphere, and we really care whether I got 0.1% or 0.2% oxygen in the exhaust stream. I mean, that just that never made sense to me. The other thing that's interesting is that before the catalytic converter, we normally have 0.3 to 0.7% oxygen. After the converter, I have zero oxygen. But yet my sensor in front of the catalytic converter can tell me I'm rich, and my sensor after my catalytic converter can tell me I'm lean, even though there's no free oxygen there. So, and that's one of the things that clued me in. It's like, wait a minute, what I'm being told and how I'm being taught doesn't make sense with what I see and how things work. And because of that, I did a lot more research, did a lot more investigation. There's a lot of kind of competing theories, a lot of kind of just BS junk out there, and a lot of bad stories repeated for 40 years. But that's actually why it happens. And that's why it's a lambda sensor. It's about how much oxygen do I need to catalyze the carbon that's available. And I figured this out because I actually built a test bench with some oxygen sensors, introduced different gases to it, and played with it to actually figure this out. So I spent some time and money actually getting to the bottom of this and doing some original research, because the data I was getting, information I was getting from experts was not good. So that's how we're working. That's why it's a Lonka sensor. That's why it generates voltage. So the less O2 in the exhaust, higher the current flow, voltage due to a potential difference in the ion concentration. So this is a little oversimplified, but it is the oxygen ions going through the wafer that generate the voltage. That is true. So the zirconium sensor just described worked well for its time, but unfortunately the type of sensor was prone to producing wide voltage fluctuations, both below and above 450 millivolts. Matter of fact, it has to in order to work. But the more important thing is it has a very limited range. It only sees 1 lambda. We're either above 1 lambda or below 1 lambda. I mean, that's all I know. I'm rich, I'm lean, I'm binary. I don't know anything other than that. And as emission control requirements got stricter, as we had the desire to be able to run vehicles leaner, so instead of being at 14.7 to 1, maybe I want to run the car at 18 to 1, 20 to 1, 23 to 1 under certain conditions where I don't have very much load. So I can increase highway mileage, lower emissions, including CO2, all that stuff. We needed a sensor that was capable of seeing a much wider range. So an air fuel ratio sensor or wideband plein air sensor can see from about 10 to 1 up to about 23 to 1 air fuel ratio. So you can see a much wider range than just you're at 14.7 to 1, you're above it, you're below it. That's all we know. So after the Cali converter, that's all we need. And it works great for that because our average mixture is going to be stoichiometric or very close to it. So my regular zirconium sensor works great after the Cali converter. And actually that tells me how long I can run lean without causing emission problems. So that's why we still use that zirconium after the CAT. But before the CAT, we really want to see this much wider range. So a new sensor was developed. This one shows a 8-pin connector, which is interesting because I've only seen them go as high as 6. But a new sensor was developed called a wideband or broadband plein air or air fuel ratio sensor. Sensor is based on the operation of the old O2 sensors discussed. The sensor is actually 2 oxygen sensors housed in one area with a common chamber between them. So what we're doing is we're going to no longer look at the voltage. Am I above 450? Am I below 450? What we're going to look at is how hard do I have to work to keep it at 450? And so we're going to measure the effort. So instead of looking at how heavy something is, instead of weighing it, we're going to measure the effort it takes to pick it up or hold it down. So, a different way of getting there. It's telling us the same information, but it's measuring it very differently. So a wideband plein air fuel ratio sensor adds 2 chambers to the original zirconium sensor. The first chamber is a diffusion chamber. So this is like a little mini trapped atmosphere that we can control the oxygen content in it. Then we have an air reference chamber. So the air reference chamber is the atmosphere, right? We've always had an air reference chamber because I have to be able to be connected to the atmosphere. And so what we're going to do is we're going to add another sensor between the 2 chambers with 2 platinum electrodes known as zirconium. So these O2 sensors are really unique in that is oxygen ions flow through them, they generate voltage. But if I apply voltage to them, I can move oxygen ions. So consequently, we come up with what we call a scent cell and a pump cell. So these plates are wired in parallel. with a circuit to the left of the exhaust stream. The two circuits sensors have a common floating ground. Anytime you say floating ground means it's not always ground. The sensor that is in contact with the exhaust stream is commonly referred to as the sense signal or sense cell, or we'll call it sensor 1 here. And the sensor connected between the diffusion chamber and the air reference chamber is commonly referred to as the ion or pump cell, which we'll call sensor 2. So during system operation, sensor 1 operates as a traditional oxygen sensor, reading above and below 450 millivolts to the PCM when the air fuel ratio goes rich or lean. The difference here is the purpose of the diffusion chamber in sensor 2 is correct the change in voltage of sensor 1 to keep it at 450 millivolts. So we're no longer looking at sensor 1 for am I rich and lean. We're going to look at sensor 2. How much current do I have to flow to sensor 2 to make it stay at 450? And what direction am I flowing that current? In other words, am I trying to hold the table down or am I trying to hold the table up? But I want my table to stay at the same height no matter what happens. So to keep sensor 1 at 450 millivolts requires sensor 2 to provide current flow, positive or negative, that will move O2 ions in the opposite direction that the sensor 1 has them moving in relative to oxygen content. If a rich mixture enters the exhaust stream, low O2 ions will flow from diffusion chamber through sensor 1 towards the exhaust stream. The voltage on sensor 1 will rise. So we have exhaust goes through. It's a lean mixture. I'm sorry, in this case, a rich mixture, I'm sorry, and goes up, and we're going to be over 450 millivolts. So what we need to do is get it back down to 450 millivolts. And what we're going to do is we are going to use sensor 2 for that. So when the voltage rises above 450, a rich mixture, the PCM reacts by providing negative current flow on sensor 2 to pump O2 ions in the opposite direction back towards the diffusion chamber, thus limited the O2 ion flow through sensor 1. So as that drops through, we have our oxygen movement, comes back through. We're high, so now the computer is going to flow current through sensor 2 through the pump. And so we're sending that through. So we're going to pump, and what we're going to do is we're going to pull the oxygen ions back the other way until the voltage is right at 450 on sensor 1. And what we're going to do is the computer, since it's applying the current, it knows exactly how much current it's applying. That's how rich or how lean we are. So we're no longer just looking at rich, lean, rich, lean. I'm able to say, hey, we're at 16 to 1, we're at 17 to 1, we're at 18 to 1. And the reason why we want to be able to do that is we want to have the computer in complete control at times when we don't want the engine running at stoichiometric. And so this really allows that wider range of control, hence the name wide range O2 sensor. When the oxygen content in the exhaust is high lean, low O2 ion content, will react in the opposite manner. Sensor 1 is going to send a low signal voltage under 450 millivolts to the PCM. The PCM sends a positive amperage signal to sensor 2 to pump more O2 ions into the reference chamber through the diffusion chamber and the exhaust stream through the plates. So if we look at this, we have a lean mixture. The animation is not perfect because obviously things would be moving less, but they're still showing them going same thing. So we have lower voltage here. Well, since it has that lower voltage, now what? The computer has to react to it. It's going to send a positive amp signal. And it's going to counteract that and bring our voltage back up to 450 millivolts. So now the computer is really just looking at how hard is it working to keep it at 450. And based on how hard it works, that tells it how rich and how lean the mixture is. So very different than our zirconium sensor. Air fuel ratio sensors are not tested with a lab scope as a rule. I do know how to test them with a lab scope. I've never needed to fix a car. I just had this discussion last night in a class. There's just no reason to. And so even though I'm a big lab scope fan, I love looking at things with a lab scope. This is one of those things that I'm going to use a scan tool to diagnose it. And I'm going to compare what it's doing to the rear sensor and some other things. I am not going to be using a lab scope on this. There's just no reason for, I've never had a reason that I've needed to do that. Even though I know how to do it, I've taught how to do it. I've always, because people wanted to know, I've always qualified it with, I fixed a ton of cars. I fixed thousands of cars and have never needed to do this. And yet I've replaced literally thousands of them. So as you can see, sensor 2 controls sensor 1's voltage by applying positive or negative current flow. The PCM monitors the current flow change on sensor 2 and makes fuel and timing corrections based on the size of these changes. There is 0 current flow on sensor 2. The air fuel ratio sensor is at stoichiometric. So that's our air fuel ratio sensor. So that's the kind of some of the magic that's happening there. We need to understand they're different zirconium sensors. Front zirconium sensors, I have to test with a lab scope to see if they're working correctly. Rear zirconium sensors, I can test with a scan tool. And air fuel ratio sensors, I can test with a scan tool. So a lot of it's knowing about which tool I need to use to perform which test. So let's take a look at the computer's logic now when it comes to fuel control. So I want to talk about speed and load cells. I want to spend some time talking about fuel trim, long-term fuel trim, short-term fuel trim, and sensor priority. So when a computer is programmed, it's programmed with what we call lookup tables. So this is how the PCM makes a decision on how to adjust fuel, ignition timing, when to turn off actuators, EGR, other things. So the PCM is programmed from the factory with a series of mathematical lookup tables. These lookup tables are similar to the multiplication tables you learned in grade school, only much more evolved. So we call these speed and load cells. The reason why we do that is that they are controlled by the engine speed and the amount of load. The load comes from our load sensor, which is either a mass airflow sensor or a MAP sensor. So using this principle, let's build a simple speed and load cell table using 2 inputs to determine the injector pulse width ignition timing for a simple theoretical engine. As the throttle opens, more air enters the engine. The mass airflow sensor records the increase in the air entering the engine. Based on the engine speed, RPM, and the math readings load, the lookup table assigns preset commands for injector pulse width and ignition timing. So we can see as I go through here at idle, I have different timing and different amount of time I'm holding the injector open compared to 1800 RPM, compared to 2500 RPM, and different amounts of air coming in. So you can see by putting those two together, 750 RPM, 7 grams per second, we end up right there. At 1800 grams RPM, 18 grams per second, we're going to be going to 2.8. I'd forgotten I had this animation in there. Actually, I think it's the first time it's worked. So this is what the computer is doing in fractions of a second as we're driving the car. So of course, there are many sensor inputs the PCM receives. The PCM, based on these inputs it receives, has to find the matching cell as close as possible. In the lookup table, the PCM issues an output command based on the selected cell to operate the vehicle. So earlier computers had much fewer cells. Later computers have the capability of a lot more cells. So I might have as few as 16 or 20 cells, or I might have, over 500 cells. It just depends on the computer and its capabilities and how much detail they want to put into the mapping. So here we can see sensor input values to the PCM. We have our ECT, MAP, IAT, TPS, engine RPM 750, so we're idling. The PCM receives the input. It decides on a particular speed and load cell. And based on the information in that speed and load cell, it'll not only set out certain commands for how much fuel, how much ignition timing, but also what actuators can be turned on and off. So an example might be something like, not only my injector, but is my fuel evaporation purging? Is my torque converter locking up? Is my EGR allowed to turn on? Am I in open or closed loop? So you can see there's quite a bit of information. So we run into problems all the time where someone puts different size tires on a car, which changes the speed and load cells. And now something like the EGR valve doesn't work. So the car fails smog. Or the car has pre-detonation issues. Because it's trying to use too much advance and the tires have thrown off the calculation because the engine speed is different for the amount of load. So we see some really interesting issues as customers modify their cars. So not all sensors are equal in the eyes of the PCM. Some sensors are more equal than others or have what we call a higher priority. The engine is very cold, 20 degrees Fahrenheit, then the ECT sensor would have a great impact on the injector on time. We need more fuel, the car's cold. However, if the ECT reading is 190 degrees, that's normal operating temperature, the ECT would have very little or no impact on how long we're holding the injectors open, because I don't need to adjust that because the ECT is just in my normal operating range. So here's a sensor priority chart for OBD1 and early OBD2 vehicles. And we have our crank sensor, cranker cam, map or MAF, which is load. Then I have throttle position, engine coolant temperature, IAT, barrel, system voltage, and my O2 sensor. So even though my O2 sensor is my primary feedback sensor, if these other sensors tell the computer to ignore the O2 sensor, it will. However, if all the other sensors are in normal operating range, the O2 sensor has a great deal of control. So on these early systems, the O2 sensor was not necessarily paid attention to all the time. On newer systems, that changes. So we still have our crank and cam and our map. Our map is our two main inputs, our speed and load. But now we have the O2 sensor right here. And the O2 sensor is looked at very, very highly. And even if and it is going to be, it's all about the O2 sensor. So even though we're using our input from my speed and load to determine which cell I need to be in, if my O2 sensor says we're doing a bad job, we're going to do whatever the O2 sensor says. Then we have our throttle position sensor, which if I put my foot to the floor, because I want to go really fast, we're going to ignore the O2 sensor while your foot's to the floor because we know we're rich. But we want to be rich because we want to go fast now. ECT, unless we're very, very cold, it really is not going to have the ability. The O2 sensor is going to bring us back to sociometric. IAT, barrel, and system voltage. So you can see the sensor priority chart has really changed. On 2000 newer vehicles, it's really all about the O2 sensor. The O2 sensor is in charge. So if the O2 sensor is not working right, the car is not going to work right. On a 2005 vehicle, which sensor has the highest priority during closed loop operation when it comes to fuel control?
The O2?
The O2, you got it. And closed loop, in case I didn't say it, or I'll say it again, means that the computer is looking at the O2 sensor, making a fuel control adjustment, and going back and looking at the O2 sensor to see how well it did. So it's that loop where we go from the engine to the exhaust system where the O2 sensors, back to the computer, back to the engine. It's constantly looping. It's a feedback loop. So we call it closed loop. So one of the other things we have on modern vehicles is what we call keep alive memory. So keep alive memory allows your car to learn. So we have our programming from the factory, it goes in our speed and load cells. But what we're able to do is we're able to learn information and save it in those speed and load cells. And the computer is going to keep that there until it loses power. That's our keep alive memory. And I don't mean losing power by turning off your key. I mean losing power by the battery going dead, disconnecting the battery, disconnecting the computer. So we call this CAM, keep alive memory. And this allows the computer to adapt to deteriorating components or conditions, sensors, actuators, worn parts, etc., and the driver's driving habits. This program strategy allows the PCM to adapt or learn to abnormal inputs and still allow the vehicle to operate within normal vehicle performance range within reason. This also allows the vehicle to maintain low emissions, even though parts are worn or have started to fail. So the keep alive memory will maintain this learned position or strategy as long as it's supplied battery power. So every car today has a keep alive memory circuit that is unswitched battery power that goes to the powertrain control module. So that powers it all the time. That's why when we replace a battery, we really don't want to lose power. So we use, battery boxes or battery jumpers that allow us to maintain power in the vehicle so we don't lose this keep alive memory. So which of the following should be done to reset CAM? Disconnect the battery. That's how we reset it. Ford is the only manufacturer in the world that allows you to reset keep alive memory with a scan tool. Obviously, we're not going to drive the vehicle or install a new one because it's just programming. So there are times that I might want to deliberately get rid of my keep alive memory, such as after I've done a repair. I don't want the computer trying to make the good part act like the bad part because the car may still run bad if I don't reset things. So I want to do that. Sometimes I'll do it for diagnostic testing to see, is this a current problem? But you need to be aware of that. The keep alive memory is why sometimes you put a battery in a car and the car doesn't idle afterwards. Well, the throttle plate's dirty. The computer had adjusted and hold the throttle plate open to make up for it being dirty, went out, lost its memory. So it's back to its original position. No air is going in the engine. The car doesn't want to start or doesn't want to idle. It's time for the computer to relearn that. So that's the keep alive memory that caused that to happen. So fuel trim. A lot of you probably heard fuel trim. Some of you may have even had a card that had a code for fuel trim. So fuel trim is the computer's ability to adjust the amount of time the injector is open in percentage. So I have my speed and load cell. I have this basic engineered, we're going to hold it open for 1.8 seconds. Fuel trim is going to modify that number by a percentage of whatever the fuel trim is. So do I need to hold it open a little longer or a little less time in order to make up for worn components? So fuel trim is the control the PCM uses over the injectors to control the mixture. The goal of fuel trim is to maintain 1 lambda. And that's a little oversimplified. It may be 0.9999 lambda or maybe 1.001, but wherever the manufacturer sets that at. So we're going to use 1 lambda here for the sake of argument. Fuel trim is measured in percentage of injector on time that is being changed from the program settings. Short-term fuel trim responds directly to the O2 sensor. So short-term fuel trim is what makes the O2 sensor go rich, lean, rich, lean. Long-term fuel trim is stored in our speed and load cells and is a learned strategy as we accelerate and decelerate and drive under different conditions that allow short-term to work correctly. So it basically smooths out the road for short-term fuel trim. So short-term fuel trim can stay in this narrow range, even though here it might need to add a lot, here it might need to take away some, but it levels it all out. So short-term fuel trim is able to operate very, very efficiently. And that is actually stored in our long-term memory. And it is stored in our speed and load cells. And that's part of our adaptive strategy that gets erased when we disconnect the battery. So short-term and long-term fuel trim add together for our total fuel trim correction. So if I have 10% positive short-term and 10% positive long-term, that would be a 20% correction of fuel trim. On the other, if I had 10% positive short-term and 10% negative long-term, that would be a 0% correction. They would countermand each other. So short-term fuel trim is directly linked to current operating conditions. It works only in closed loop. Long-term fuel trim works all the time, both in open and closed loop, because it's a long-term strategy. It's what we need to know when we're here. So I have a little chart here, and this is a theoretical chart because it has a range of 100%, which mathematically that's what we have. No manufacturer uses that much. So I have short-term and long-term fuel trim, and short-term and long-term fuel trim usually operate within a plus or minus 10% range when there's no engine performance problems. Modern vehicles will work in a plus to minus 5% range. They've gotten much better at it. So here is long-term fuel trim. Oops, I didn't wait for it. So there's long-term fuel trim. I want to see short-term fuel trim pop up. Short-term fuel trim will go back and forth, and it's going to switch because it's making the O2 sensor go above 1 lambda, below 1 lambda, above 1 lambda, below 1 lambda, or rich lean if I want to think of the oxygen sensor. And so when the engine goes rich and short-term fuel trim subtracts fuel to correct that, long-term fuel trim will move in order to get short-term fuel trim back to zero, because we want short-term fuel trim to move right around that zero range all the time, no matter what speed and load cell it's in. So each speed and load cell, long-term fuel trim will move to compensate for what we need. So for example, if I have a problem where I'm not supplying enough fuel at higher RPM because of low fuel pressure, I might need to add more fuel trim at high RPM, but I'm fine at idle. I don't need to do anything there. So long-term fuel trim might be big at high RPM, high speed and load, where low speed and load, it's not adding anything, but it allows my short-term fuel trim to stay operating in that same area. No. So O2 sensor sees rich, O2 sensor sees lean. We got our percentage. There's my long-term fuel trim. And we're switching back and forth. So our fuel trim monitor monitors how well we're doing on this. When it gets too high, we set a code like a P0 171, 174 code, 172, 175, telling us that we're having to add or subtract too much injector on time. And that's what sets the code. So we're switching back and forth. And this is a more realistic range, plus or minus 25%. And now it's shifted negative. It's taken away injector on time. And long-term fuel trim will move to get short-term fuel trim to come back to zero. And it remembers that. So next time it goes to that speed and load cell, it's already going to have that long-term correction there. It's ready to go. So short-term fuel trim is only used under which of the following conditions?
Closed loop,
Closed loop, you got it. What is the maximum fuel trim values will normally be considered acceptable? I did say it. Okay, it's plus or minus 10%. That's what's normally considered acceptable. If I'm above 10%, I know I have a problem. If I'm working on a newer vehicle, some newer vehicles are down as low as 5%. So even 8 or 10% may be a concern. But anything over 10% is always a concern. And thank you, Miguel. I didn't see the chat right at first. So here's an example of fuel trim working. So here I have a scan tool capture. I've got engine speed, short-term fuel trim, long-term fuel trim, and my air fuel ratio sensor. So short-term fuel trim values are volatile, meaning they are erased each time the key is switched off. Long-term fuel trim values are long-term adaptive strategy, which means that changes based off a short-term fuel trim and will adjust to changes based off all operating conditions over a period of time, such as wear and tear on the engine and subsystem. So if we take a look here, here's my air fuel ratio sensor, and it goes rich. So here is where I mentioned that air fuel ratio sensors read opposite of zirconium sensors. So an air fuel ratio sensor, a low signal is rich, a high signal is lean. They read exactly opposite of a zirconium sensor. So it doesn't matter whether I'm looking at voltage, which I'm looking at here, or if I'm looking at amperage flow, low or negative is always rich, high or positive is always lean. So in this case, the sensor goes rich, and we see that short-term fuel trim instantly responds. It moves first. So my sensor moves, short-term fuel trim moves. Then long-term fuel trim moves. Now, as long-term fuel trim moves, we see the sensor start coming back up. I'm having to fight it. I've actually created adding propane here in order to try to get it to go rich. So you see the computer's compensated for the propane I brought in, and it did it with long-term fuel trim. And as long-term goes down, short-term fuel trim starts to come back up. And then I add a little bit more propane, and I'm able to get short-term fuel trim back down. Long-term fuel trim is down, and eventually I'm able to pull the sensor down. And then you can see right here, I release the propane, it goes back up. Short-term fuel trim goes not only back to the 0 point, but goes up very positive, plus 20. I'm plus 20 here, negative 22 here. This comes up as this goes down, and we both end up at pretty good numbers. So we're close to 0 here, and I'm at 6.8 positive over here. So you can see where they work together. So if short-term fuel trim goes high, long-term fuel trim is going to go up and try to fix it. So you can see here, this is a nice example of how they come together back towards 0, how they can cancel each other out. Here's where they're learning. This is where they both went negative. I took away the propane, so now the car is running super lean. O2 sensor sees that, or the AF sensor sees it. Short-term fuel trim immediately responds. It goes up to its maximum of 20%. Long-term fuel trim moves in order to bring short-term fuel trim back down to a normal operating range. So that's the relationship between our front sensor, short-term fuel trim, and long-term fuel trim. So the PCM determines the short-term and fuel trim, long-term fuel trim are at their maximum values, and an air fuel ratio imbalance exists, such as caused by a vacuum or injector leak, it will store a fuel trim related DTC or diagnostic trouble code. After establishing loop status of the vehicle, evaluating scan tool data, along with a 5-gas analyzer, determine if the PCM is providing a rich or lean correction and the extent of any such correction. So let's look at a vehicle, and this is kind of cool because Chrysler on their factory scan tool actually will show us the speed and load cells on the car. They're the only one that does. But let's see how adaptive strategy in action on the next 5 scan tool screens. We will use fuel trim cells for a 2000 Dodge Intrepid with a 3.5 liter as viewed on a Chrysler factory scan tool. So here is the scan tool data. We can see the engine speed is 795 RPM. The injector pulse width is 2.8 milliseconds. The vehicle is currently in open loop. My long-term fuel trim is negative 4.1%. And that comes because we are in speed and load cell C12, where it says we're going to take away 4% anytime that I'm in C12. That's in memory there. So it knows anytime we go into cell C12, we need to take away 4% long-term fuel trim. Because we're in open loop, you'll see that our short-term fuel trim is at 0 because it's not being used because we're in open loop. So down here, we have all of our speed and load cells for this vehicle. We have our oxygen sensors up here. I have my short-term fuel trim here, and long-term fuel trim is behind it. So let's take a look at this a little bit here. So on this next screen, the engine RPM increases above 1900 RPM. Long-term fuel trim moves to the upper row of cells that have been adopted to previously learned condition. Note cells C4 and C5 are inductive of a load and RPM that would be used during an emissions test. So now I'm at 1900 RPM. We have moved over to cell C5, negative 3% long-term fuel trim. We can see long-term fuel trim right here, negative 2.9. My short-term fuel trim is now negative 6.2. So in total, I'm taking away 9.1% of my injector on time. We can also see when looking at my O2 sensor, my O2 sensor is at 760 millivolts. So short-term fuel trim will continue to go negative until that drops below 450 millivolts. Then it'll start coming back up. If it spends too much time negative, then long-term fuel trim will move. So it saves it there for future use. And this card had its memory reset not too long ago, so it's still learning. So here's an example. On the next screen, we see the results of a major fuel trim correction, but the technician installed a new part, but did not reset the adaptive strategy. The PCM is using a learned value from the bad part, plus 13% in cell C8. Since the problem has been corrected, the long-term fuel is now overfueling, and short-term fuel trim is making a major correction of negative 14% to adapt to the situation. So I will do this on purpose a lot of the time. So here I can see that my strategy is a plus 13, so long-term plus 12.7%. Short-term fuel trim negative 14. Well, if I subtract 12.7 from 14, I'm at what? Negative 1.4% is my net. I think we fixed the car. So I'll do this a lot when I put a part on, so I can see if I fix the car or not. Then I'll clear the strategy out before I give it back to the customer. But the advantage of doing this after I replace a part to see if I fixed the car or not is that if I reset everything to 0, I have to drive it and drive it and drive it. And I keep asking myself, is it done learning yet? Is it done learning yet? Is it done learning yet? And I might give the car back to the customer when it's not done learning. The check engine light might come back on and I might get the car back with an unhappy customer. By doing this, I can see that the part that was replaced, my long-term strategy was negative 12.7. We're now taking away 14.1. I fixed this car. There's not a doubt in my mind. Now I can clear the strategy. I don't need to go on a long extended test drive to relearn everything to see if I fixed the car, because I already know I did. So this saves me a lot of time, as well as gives me a higher degree of certainty that I fixed the car. So understanding the short-term and long-term fuel trim add when I'm fixing a fuel trim related code, I'm going to many times put the part on, start it up, see what the correction is, see if my correction accounts for all of my problem or only part of my problem. If it's only part of my problem, now I know I have another problem I have to diagnose. And it's a much quicker, more efficient way of doing that. So, oops. Okay, no, that's fine. I'll take a couple cycles to test drive the system to adopt and install part. So even if I don't clear it, if I drive enough times, it will relearn. Next screen, we'll see the vehicle is decelerating and all the fuel trim has been cut to 0. So in this case, this is what's called fuel cutoff decel. So since we're decelerating, we've turned the injectors off. My O2 sensor is reading basically 0 volts, and my short-term fuel trim is not active. And so all fuel injected vehicles today do this. It's called fuel cutoff decel. So when you let your foot off the gas and your car is decelerating, you're actually not putting any gas in the engine. All that you're doing is spinning the engine over. It's an air pump. It doesn't put gas in it until we get down below a certain speed or until you touch the throttle. So this has been a strategy for many, many years. It's called fuel cut decel. And we do that for emissions. And older carbureted vehicles, carburetors ran dirtiest under deceleration. High vacuum would, on a low engine speed, would pull a tremendous amount of fuel into the engine, causing huge emissions. So that was something that fuel injection corrected by turning off the injectors when we decelerate the engine. So the next screen, oh, come on. So the next screen, we see that the technician has reset the adaptive strategy fuel trim memory via the scan tool. Note that all the long-term fuel trim cells are now 0. System will reset. The vehicle driver may notice the vehicle's throttle response may now be sluggish until the system has time to relearn. So here they've all been reset to 0. So we can see we have a 0 value for all of our speed and load cells. So if I did this after I put a part on, I would need to drive the car and wait and see. So if I am trying to fix a problem that, gee, it was at plus 13, okay, so it goes up to plus 1. Then it goes to plus 2. I drive it some more, I get to plus 3. Well, is the car fixed and it's going to stop at plus 3, or is it going to keep going? I don't know. So I got to keep driving it. Does it get to plus 4? Does it? So you see where resetting the adaptive strategy and then going to drive the car to look at the data can be much more time consuming than let the data try to self-correct, use the secret power of math and understand a positive and negative integer and be able to figure out where they equal out at. Then I can quickly determine, is the repair I did enough to compensate for the entire fuel trim correction or only part of it? And then I can, with high confidence, know very, very quickly without an extended test drive that I fixed the car. So as you can see, if the input sensors like MAF, TPS, ECT, IAT, et cetera, are incorrect, the PCM will still try to match the erroneous inputs it receives to the closest matching cell. Due to a bad sensor input, the cell selected by the PCM may not be appropriate for the actual operating conditions of the vehicle. The vehicle may now experience an emissions failure drivability problem. So an example here is a wrong cell was selected by a PCM using a bad mass airflow that would not allow EGR activation. Thus, the vehicle failed the NOx portion of the smog inspection. If the correct cell were selected, EGR would have been activated and the problem would not be present. So long-term and short-term fuel trim is divided into what categories?
Speed and load.
Speed and load, you got it. Speed and load. So scan tool data, not all manufacturers display speed and load cells for the technician. Matter of fact, most don't. Some aftermarket scan tools can unlock the cells through the use of fuel trim data by mapping the throttle position compared to the engine RPM and inserting the fuel trim correction. The cells can become evident as shown on the next slide. So in this example, this happens to be a vehicle we were working on that the customer complained of low power going up hills. And we have our throttle position and my engine speed. And I can see here at low throttle position, I have green numbers, means I'm within that 10%. As I start accelerating the engine using more engine speed and more load, we go from orange to red. And we do this on both banks of the engine. So whatever my problem is has to affect both banks of the engine. So it can't be an injector. It can't be something that only affects one side of the engine. It has to be something that affects everything. And on this vehicle, this happens to be a speed density vehicle. This was a Chrysler. The first thing that comes to mind is fuel pressure, fuel supply, because fuel affects both sides of the engine. And unlike a mass airflow sensor, where a bad mass airflow sensor can cause a car to run lean and have low power, a MAP sensor car won't normally fail that way. At the same token, so this allowed me to quickly, with one test drive, to not only duplicate, wait a minute, here's what's going on. We are running lean or compensating for a lean condition. At the same time, I have no power going up a hill. This is a fuel problem. This is not a plugged exhaust problem. This is not a single injector problem. So with one test and being able to map this, I could very quickly on just one test drive know exactly what my next test had to be. So it just excluded anything else that could be wrong. Here's where I need to go. I've either got a plugged fuel filter, bad fuel pump, something like that. I need to check my fuel delivery. Correct lambda ratio is obtained by which of the following?
All of the above.
Great job. All the above. Absolutely. This all works together to make the magic happen. And so O2 sensor testing, I have instructions in here in the PowerPoint for O2 sensor testing. We warm up the engine, run the engine speed at 2000 RPM for 2 minutes, return the engine to idle, add propane, remove the propane, and then quickly snap the throttle as soon as the sensor drops down below 175 millivolts, and use the cursor to measure the rise time. According to the state, it needs to be under 100 milliseconds. From practical purposes, I expect to see about 35, 36 milliseconds. So we would set the scope at a 5-second timeline, 0 to 1 volt scale. And I can see the sensor switching. I happen to be on 2 volts on the screen, but I see the sensor going rich lane, rich lane. I would use the freeze button to freeze the capture when I get ready to measure. So here we're idling. I add propane, which is going to make it go rich. I take away the propane, the sensor goes lean, and I quickly snap the throttle. And now I'm going to measure how fast it rose from under 175 to over 800. So here's a review of what we just did. I've got my mass airflow sensor, my throttle position sensor, my injector pulse width, my short-term fuel trim, my oxygen sensor, and my RPM. So I had our high RPM to warm everything up, let it come back down to idle. Then I added propane right here. As I added propane, the sensor went rich, short-term fuel trim went negative. I took away the propane, the sensor goes lean because the computer is now under fueling. And then I quickly snap the throttle, which you see on the TPS, which dumps a whole bunch of fuel into the engine, which causes the O2 sensor to rise. And that's the rise that I want to measure. So I would use my cursors for that. So we have 2 cursors. I have cursor number 1 right here and cursor number 2. And these cursors are going to intersect the line. And where they intersect the line, it's going to give me the voltage in the box here. So cursor 1 is intersecting at 380 millivolts. Cursor 2 is intersecting at 190 millivolts. The delta time is the time between the two cursors, in this case, 1.67 seconds. Delta voltage is the difference in voltage between the 2 points. And again, just showing the intersection point and my delta time. So what I want to do is I want to move the cursors to measure. So I want to see, can the sensor go over 800 millivolts? And cursor 1 over here shows 940 millivolts. Cursor, and next question is, can I go under 175 millivolts? And cursor 2 shows I'm down at 170 millivolts. So the sensor passes the first part of the test. It can go over 800 and under 175. Now I need to see if it goes up fast enough. So now I'm going to bring the cursors as close as I can and measure the rise time. In this case, I have 107.6 milliseconds. That's too long. So what I'm going to do is I'm going to try to move the cursors closer together and still keep them under 175 and over 800. So now I just move the number 1 cursor a little closer, and you can see I'm now at 180 millivolts, not a valid measurement. So even though my time went down slightly, the measurement's not valid. Now I'm back to where I started. So I can move the other one. I can move cursor 2 a little closer, but oh, it dropped to 790 millivolts. So even though my time went down, it's not a valid test because I'm not going over 800. And so when I look at the final result, it's a very bad sensor. So I can also test without propane. If you don't have a propane rig, I can warm the engine up just as I did before. I can raise the engine up 2000 RPM, and this only works on fuel injected vehicles because I know fuel injected vehicles turn the injectors off when I let off the throttle. So I raise the throttle. As soon as the O2 sensor voltage, release the throttle. As soon as the O2 sensor voltage is below 175 millivolts, I'm going to snap the throttle, freeze the screen, and bring the cursors out. And like I said, a good sensor will be 35 to 40 millivolts, 35 to 40 milliseconds. If the rise time is under 20 milliseconds, it's also bad. So if we look here, I'm looking at 2 O2 sensors. These are both front sensors, and they should cycle at the same range, speed, and amplitude, which is not quite doing here. Sensor number 1 in yellow is not looking great. And then I'm going to come down off 2000 RPM. It goes lean because the injectors turn off when I let go of the throttle. And then I quickly snap the throttle. And we can see very clearly here that sensor 1 never got below 175 millivolts because this is 200 millivolts right here. So sensor 1's bad without even getting the cursors out to measure it. I can bring the cursors out. Here's another car, 35 milliseconds. So I brought these as close together as I can. In this case, I'm at 60 millivolts and 940. Because if I go any closer, I'm going to go below 800 or above 175. So the fact that I'm from 60 to 940 is fine. I'm as close as I can without violating the rules. Here's another one I measured. In this case, I was testing 2 sensors at the same time. Sensor 1, 36 milliseconds. Sensor 2, I don't even need to get the cursors out because, gee, it was slow to start, and then it took way too long to come up. So I can tell right away sensor 2 is bad. Here we're measuring both bank 1 and bank 2. And I can see here 143 milliseconds, sensor's bad. Here I measured a sensor, 18 milliseconds, which is too fast. I put a new sensor in, 36 milliseconds, which is the correct speed when you test them. Here is what bank 1 is, what the old sensor looked like at 2000 RPM, which according to the book is good. This is where the book is wrong. According to say it's switching, I've got 11 cross points, 5 seconds. It's meeting the criteria the book gives you. Here's where a sensor that I put in that's the correct speed, but is actually half the speed of this sensor when I test it. But look at how much more activity I have at 2000 RPM. The reason for that is the clock speed in the computer has to be matched to the speed of the O2 sensor. If the O2 sensor is not at the correct speed for the computer's clock speed, then it delays the switching back and forth, which makes the catalytic converter less efficient. So even though the book talks about raising the engine to 2000 RPM and looking at the sensor to see if it's good, that's not a valid test. All that tells me it has activity, and it tells me it's able to range potentially. But even if it doesn't range at 2000 RPM, doesn't mean that it's a problem, because it could be fuel trim that's not ranging it. So that's another reason why that's not a valid test. Where we're doing this, we're taking fuel trim out of the equation. I'm separating fuel trim from our converter from our fuel trim by just testing the O2 sensor. I know it's going to turn off fuel. I'm doing a snap test. So no matter what my fuel trim is, if it's plus 40 or if it's 0, it doesn't matter, because I've taken it out of the equation of testing. On the other hand, if I test it this way and just look at activity, a fuel trim problem or a vacuum leak is going to make an O2 sensor look bad. There's nothing wrong with the O2 sensor. So that's another reason why this is not a valid test, even though the book talks about it. And you can see here with a sensor that's slower, but the correct speed, it switches a lot better because it's the correct speed, it's the correct sensor calibration. So with that, we made it through fuel control. So we are all set. So we're going to get into computers next week and dive into computers. And at this point, it looks like that's going to be on Tuesday, but I will send an email out and confirm that with everybody. So have a great rest of your day.